Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin. I'm going to cover unit tangent vectors. So let R of t be a vector valued function. Then t, which is going to be this unit tangent vector, is defined by dr over ds, where r is going to be, this vector that we set up here, and ds is going to be the differential of its length, of its arc length. So really what we're trying to do is, in order to find the unit tangent vector through this definition, it says we're talking about how its direction changes over its arc. And that's what we're saying here. So this is, this is the position function. So how is its position changing with respect to its arc? So we can see that here it would be this, and then so on and so on. So this is going to be equal to t. Now, calculating something with a ds on the bottom is not how we compute it. So what we need to do is we need to use the chain rule to be able to rewrite this in terms of just its parameter t. So the length of the curve L is given by the integral from a to b of the magnitude of v of t dt. And then we have this s of t function here, which really is kind of, well, it's the accumulation function for the arc length. So if I have some point here, which say this is at t naught, then its length that goes from here all the way up to, say, some t is going to be a value. Now, if I change this value t to maybe here, now it's going to be a little bit longer, or to here, it's now going to be a little bit shorter. Now, what we're doing is we're making t not a constant, and this t is going to be where we're sliding, or basically what we're accumulating to. So s of t is going to be the accumulation function of this length. So when I need to take the derivative of s with respect to t, because I have the differential ds here, I'm trying to find this differential, or at least make it useful for us. So what I can do is ds dt is going to be, well, this is the derivative with respect to t of this original function. So the derivative with respect to t of the integral from t naught to t of the magnitude of v of tau d tau. The reason why we say tau instead of t is because the upper bound of this integral is already named little t, so I can't put t's here as well. So this is still represented as the parameter of our function. So using the fundamental theorem of calculus, the derivative of the integral from a constant up to its variable is just going to be this variable in this position, in its input position. So this is going to be nothing more than the magnitude of v of, well, this variable. Okay, so now what I can do is I can resolve this t, is that, t is equal to, well, we said dr ds. Now dr can be written as dr dt, or I should say dr ds can be written as dr dt all over ds dt. And using the chain rule, you can see that those dt's will go away, or at least I could say that this is equivalent to this using the chain rule. They don't really cancel, but mathematically it looks like that. So our dr dt is going to be equal to, well, this is the derivative of r with respect to t, so this is just v of t. And then ds dt is equal to the magnitude of v of t. So a lot of times we say that the unit tangent vector is your velocity vector over the magnitude of the velocity vector. And this really guarantees that this is a unit vector because I have a vector over its magnitude. And then you can also see why it's kind of its tangent vector as well, because the tangent is going to go in the direction of the curve. So if I look at t here, say this blue curve is like some train tracks, and it leaves the tracks here, it's going to move, tangent to that particular curve. Now, the velocity moves parallel to the curve, so the unit tangent vector is going to be parallel to the curve, but of unit length, and that's really what I have here. It's parallel to the curve. Just to make sure you can understand what I mean by that, is this is 1 over the magnitude of v times v. So this is nothing more than a scalar, and this is definitely parallel to that curve. So this is the unit vector parallel to that curve. And the way we compute it again is going to be this piece here. So erase and kind of just say this is how we compute it. So let's compute a couple unit tangent vectors for some curves. So we're going to determine the unit tangent vector to this particular curve. And I know that in order to find t, that t is defined by v over the magnitude of v. So I'm going to have to find the velocity vector, and then I'm going to have to find its magnitude, and then I'll divide those two. So v of t is dr dt. So it's the derivative of this curve. So the derivative of 2 cosine is going to be minus 2 sine ti, plus the derivative of the sine of t is going to be, this is going to be 2 cosine t j, plus the derivative of this linear piece is just going to be that coefficient root 5, and this is going to be k. Now I have to find its magnitude, so the magnitude of v of t is going to be equal to the square root of the sum of the squares of its components. So this is minus 2 cosine t squared plus 2, sorry, this should say sine, try that again, sine t, 2 cosine t squared plus our root 5 squared. So this is going to be equal to, well, you can see a Pythagorean theorem is going to come out of this. So we're going to have 4 sine squared t plus 4 cosine squared t plus 5. And I can factor a 4 out of this, well, out of the first two terms. So this is going to be the sine squared of an angle plus the cosine squared of the exact same angle plus r5. And we know that, this is going to be equal to 1. So this would be the square root of 4 plus 5, or the square root of 9, which is equal to 3. So that's our magnitude of v of t. So finally, our unit tangent vector is going to be equal to this, velocity vector over its magnitude. So minus 2 sine ti plus 2 cosine tj plus root 5k, all divided by 3. Which is the same thing as, multiplying each one of these components by a third. So I can put, the 3 on each one of these components because it's nothing more than a scalar. So minus 2/3 sine ti plus 2/3 cosine tj, and then plus root 5 over 3. Okay. Now, as an exercise for you, find this thing's magnitude and just double check it's 1. So, and it will be. All right, so one more example, and then that'll be it. So here's our last example. I want to find the unit tangent vector of this curve. Well, this curve, we're talking actually a line here. So the unit tangent vector should be, we'll see, it's going to be, you'll see. So in order to find a t, what I know I'm going to have is I need to find v of t first. So I'm going to have to find the derivative of this thing. So the derivative of the first is going to be, well, this is linear, so it's going to be the coefficient in front of t. So this is 1i. Be careful of this negative sign. They like to do this in all your calc books. That this is the same thing as negative t minus 1. So I could write this as plus a minus t minus 1 as far as that coefficient. So the derivative is going to be, minus 1j. And then similar, the derivative of this is just going to be 1k. So what I know is that this, this velocity vector is going to go parallel to this curve because remember this line has, parallel direction of really the coefficients in front of t. So 1, negative 1, 1. Unfortunately, this is not a unit vector. This has length 3, so I have to divide by its magnitude. So the magnitude of v of t is going to be the square root of, the squares of these components, or the sum of the squares of these components. So that's how I got that root 3. So I know that the unit tangent vector is going to be equal to, this vector over its magnitude. So you can write that vector and then distribute the 3, or the root 3, to all 3 of these. Sometimes they write it like this. Sometimes they distribute it. It really doesn't matter. We know that this is equivalent. So 1 over root 3j plus 1 over root 3k. So either are equivalent, which is fine. So if you like the content, please consider liking, subscribing, and sharing. Thank you.